We're good? Okay, welcome everybody to today's special lecture co-hosted by the Grantham Institute and the Energy Futures Lab here at Imperial College. My name is Martin Seeger. I'm the co-director of the Grantham Institute here at Imperial. We've convened this event to hear about the results of a significant new analysis of energy technologies to discuss sustainable energy for urban areas and to bring together people who consider these issues in research, business and policy making. As two of Imperial College's global challenge institutes, we work together to maximise the impact of the college's research, education, innovation and influence. At the Grantham Institute, we focus on climate change and other environmental issues, and at the Energy Futures Lab, our colleagues aim to tackle a broad range of global energy challenges. Now, today, I am delighted to welcome back Kamel Naceur, the International Energy Agency Director of Sustainability, Technology and Outlooks. We were pleased to hear from him in February with the results of the IEA's flagship publication, the World Energy Outlook, which has given us plenty to think about over the course of the last few months. Today, Mr. Naceur will present the latest findings of the Energy Technology Perspectives, an influential report that is highly regarded around the world. He has a few copies for people you can take as you leave. The headline statement from the 2016 report shows that decarbonising urban buildings and transport is key to attain Paris climate goals. But slow progress will test the government's commitment. I look forward to hearing more about what we can in the room do together toward these goals. Before I hand over to our speaker, I'd like to draw your attention to two of our recent Grantham briefing papers in which we present topics of research in a format relevant for policymakers and businesses. One covers the role of electrical energy storage technologies in mitigating climate change, and that is literally hot off the press. We're getting a box of these delivered to us by 10:30. Serious, and they'll be outside, ready for you. And another is a collaborative publication by Imperial College students on air quality in urban areas, and we have a few of these as well, and we will be presenting those for you, and you can collect those outside. So I hope you find these interesting and useful, and we look forward to discussing these and the subject of sustainable urban energy systems with you in the future. But now, please join me in welcoming Mr. Kamel Naceur.
Yeah. Good morning, everyone. Can everybody hear me? Yeah. So thank you, Martin, for the kind introduction. It's a pleasure to be back at Imperial College. I used to live a few years here in London, and certainly my wife thinks this is the best city where we have ever been. So it's always a pleasure. So I'll be talking about the Energy Technology Perspectives. Martin mentioned a sister publication called the World Energy Outlook. These are the two main publications of the IEA that are looking at long-term outlooks. The World Energy Outlook looks at it more from market standpoints and goes to 2014. The Energy Technology Perspectives looks at it more from a technology perspectives and goes to 2050. So this publication, ETP 2016, came out in June of this year, last month. And there is a special connection with Imperial College because one of the directors of the IEA that was in charge at that time was the person who actually launched the ETP, the first edition 10 years ago, and that was Dr. Naceur, who I'm sure many of you know. And Neil had a remarkable career with the IEA, and he's now with Imperial College. So 10 years of ETP. The theme this year is urban systems, and I will explain in a few minutes why we decided to focus on urban systems. But let's look at 2015 in terms of what it brought to the energy systems. I think that, I've been 35 years in the energy sector. It has been the most extraordinary year in terms of developments. The first major development actually happened in New York in September 2015, where at the United Nations there was the adoption of Sustainable Development Goal number 7, which was to provide energy access to the widest range of people by 2030. SDG 7. It's extremely important. One of the reasons is that today 1.2 billion people around the world don't have access to electricity. And about 3 billion people don't have access to modern energy systems. So this SDG 7 and September 2015 will remain a very important date for the energy sector. But there were also other things. Of course, COP21 was the second largest event. But I will talk about some trends. I think we're having some. There are some signs of decoupling. We call it a happy divorce between economic growth and emissions growth. And there are not many happy divorces, but this one is a good one. We saw the emissions of CO2 related to energy remain flat, despite a worldwide GDP growth between 3 and 3.5%. So that is remarkable, and we will see why in a second. And this follows 2014, where we haven't seen also the same trend of growth that we had before. So if we look at over the last 4 decades of emissions from the energy sector, what do we see? There were mostly 3 periods where we had emissions decline. The first one was back in the late 70s, early 80s, when we had the second oil shock after the Iran Revolution. The second one after the 90s, after the dissolution of the Soviet Union. And the third one was the global financial crisis of 2008, 2009. But apart from that, we generally saw a coupling of economic growth and emission growth. So that was up to 2013. 2014, what we see is actually the emissions did not grow at the same speed. We go back again to 2015, and emissions were at the same level. So that is quite a remarkable achievement. And why do we see that? Is first, the Chinese economy is being transformed, is going from an industrial production slash manufacturing into more a service related growth. The second one is the growth of renewable. And the third one is energy efficiency. So these 3 have combined together to have this trend of emission stalling. So that is a very good sign. The second indicator that we follow is the renewable capacity addition. And there was a very good signal, is that for another year, there has been a record growth of renewable power capacity. And we have reached an additional 150 gigawatts in 2015. And so we look at the trends. These are the trends of renewable capacity around the world. What we see is that China has been taking over as being the biggest implementer of renewable capacity. But we see this growth going over the last few years. What do we see going forward is we see another growth, and we have the potential of going from 140 gigawatts to 170 gigawatts. So this is quite significant. Why? Because this represents more than half of the capacity, of the additional power capacity. So we have some room to go, and this is post-COP21, between the announcement and the potential. So we have to make sure that we follow on those trends. Then COP21, as you are all aware, has been a major event in terms of changing the perspectives, of gathering the momentum from a bottom-up approach to the INDCs and now the NDCs. There are new goals going forward. Now, does that mean that we are going to hit home base, as the baseball players would say? We will see that we will not be at the level where we want to be. So, how do we go from there? There are other things that we are also looking at, is what happens post-Paris Agreement. Paris Agreement has set up, through the NDCs, some expectations in terms of emissions growth. This is what we call the 4DS, pretty much 4-degree scenario. In that NDC scenario, what we see is that the emission will not decline, and actually the emissions from the energy sector will continue to grow. And we will go from the 35 gigatons to a 42 gigatons. If we don't do anything, we will be above the 50 gigatons. If we want to be in a 2-degree, and this is our 2-degree scenario, we need to be much less. So instead of growing, we need actually to halve the emissions, or more than half the emissions. We need to go to about 15 gigatons from the 35 gigatons. So we need to decline, compared to the Paris Agreement objectives, by 20 gigatons. How do we do that? This is through what our colleagues from Princeton, University of Princeton, have called the decarbonisation wedges. And these are, the decarbonisation wedges are technologies, energy technologies, that would reduce the carbon intensity. What are these decarbonisation wedges? The first one is renewables. Renewables represent 32% of the efforts, additional efforts that we would need to have. The second one is energy efficiency, using more efficiently the energy than what we are doing today. And then third one, quite interestingly, is carbon capture and storage. So you all know that there have been some turbulent stories about carbon capture and storage, especially in UK, among other things. So in theory, carbon capture and storage could be the third biggest decarbonization wedge. The fourth one is nuclear, and the fifth one is fuel switching, switching from coal to gas. So these are the discrete energy systems that would help the decarbonization to a 2-degree scenario. If we take renewable energy efficiency and CCS, this represents about 80% of the effort. So you may ask, what if we didn't have one of those technologies, let's say, for those that don't like nuclear or that don't like CCS, what happens if you don't have that wedge? So the answer is that it would cost significantly more. So the IPCC assessment report number 5 has indicated that the system would be about 139% of the cost if we didn't have carbon capture and storage. So it's extremely important that we have those decarbonization wedges there. We could have only renewable and energy efficiency, but this would be much, much more expensive than the solutions that are being proposed here. So that was the NDC scenario. There is also the business as usual scenario, which we call the 6DS. And what we see is that from the 6DS to the 2DS, we have the actually a mix of technologies. Then the efficiency becomes number one, and then CCS becomes the third one with 12%. Where are these technologies going to apply? First one is renewables in power, in the transport, and in the building sector. In terms of CCS, this would be applying not only to the power sector, but it's also going to apply to the industry, and there is a lot of work that needs to be done by the industry to use CCS. And then in the transformation, which is refineries and petrochemicals. The third one is fuel switching from coal to gas, and this would impact the power sector, the industry sector, and the transport sector. Energy efficiency would apply through a little bit through power, but mostly through industry, transport, buildings, and transformation. And then finally, nuclear would apply only to power. So these would be from the generation side to the end-use side, how those wedges would apply. So the other things is that from an end-use side, all the sectors are needed. We need to have the industry, we need to have the power sector, we also need to have transportation, we need to have buildings, and they represent 94% of the efforts. So what happens in terms of primary energy sources between those different scenarios? Today, oil is the number one source of primary energy, followed by coal, and then followed by gas. Number 4 is biomass and waste. So these three together, the fossil fuels represents 81% of the primary energy sources. If we go to a business as usual scenario, if we don't do anything, if we don't apply the technology, the NDCs that were promised in Paris, what would happen is that by 2050, the number one source of energy would be coal. So, quite an interesting development. Oil would be number 2, gas would be number 3. Renewable will grow, but there will still be distant number 5, and will be still at the 80% for the fossil fuels. What happens if we apply the NDCs? So with the NDCs, what we see is that oil still remains number 1, coal is number 2, about the same level as gas, and then this is followed by biomass, and we see more growth of renewables. So what happened in a 2-degree scenario? In a 2-degree scenario, what we see is that biomass and waste and renewable would be number 1 and number 2, and they would displace oil as being the largest primary sources of energy. And oil would be number 3, followed by gas, and then coal would be about the same level as nuclear. So this would be a complete transformation of the energy sector. We will go from 81% fossil fuel today to 45% fossil fuels by 2050 in a 2-degree scenario. Can we go to 0? We could go to 0, but the cost would be way, way higher, and there are also issues with energy security. So in this publication, so I have an executive summary here, and we have a few over there, but it's also available for free download on our website. We're also tracking the progress of the clean energy. And we have a traffic light indicator for the technologies to show, are we on track with a 2-degree scenario? And what we put in red are technologies that are far from being on track. And this is including the coal-fired power plants. Today, still a number of new coal-fired power plants are using older technology like the subcritical technologies, while we should be moving to ultra supercritical or IGCC that have much higher efficiency. Carbon capture and storage has a red status. Between 2008 and now, we didn't see these 20 mega projects that were announced, and we need to go back on track. Biofuels are not on track, and buildings are not on track. With an orange indicator, we have a number of technologies, including nuclear, the transport, the industry, and appliances and lighting and energy storage. These are in orange status. And then in green status, we have essentially the electric vehicles in terms of growth, and the solar PV and onshore wind. Electric vehicles actually in 2015 has surpassed the 1 million electric vehicles around the world, which is still very, very little. It's 0.1% of the vehicle fleet. But you go to places like Beijing, for those of you who've been to Beijing recently, and one of the things that impressed me the most was that the motorbikes are more and more electrical motorbikes. You have hundreds of thousands of electric motorbikes in Beijing today. In terms of solar PV and onshore wind, we have seen the new capacity from those, but we have also seen very interesting development in terms of cost. These are some recent auctions of electricity that have been around the world, and we're putting on yellow the solar PV, photovoltaic, in terms of dollars per megawatt hour. These are long-term contracts. And what do we see? The blue is the wind onshore. Very interestingly, and this is around the world, in 2013, so only 3 years ago, the purchase price of electricity in Jordan from solar PV was $120 per megawatt hour, 120. You see quite a significant decline, and actually the most recent prices are at $30 per megawatt hour. So, and these are prices in Morocco, prices in Mexico, and so the prices within a 3-year range, we have seen a factor of 4 in decline in wind related, in solar prices. In terms of wind, we see a similar trend, perhaps not at the same magnitude in terms of drop. We were at $80 in South Africa in 2013, and now we are about $30 per megawatt hour. And offshore wind, we have recently seen prices around $80 to $85 per megawatt hour. So we are seeing quite a significant decline in renewable electricity prices. And this is now competing with the fossil fuels based electricity. So let's move now to the focus of the publications, which is urban systems. Why did we look at urban systems in this publication? If we look at today in terms of what is the percentage of urban population compared to the total, we are at about 50% worldwide. And by 2050, which is the date of projections for this study, we'll be at 70%. We'll go from 50 to 70%. And so that is quite a remarkable increase. The other thing that is very important is that in terms of energy usage, the urban population uses much more than the non-urban. So they represent almost 80% of the energy use, and they represent a similar share of the emissions. If we look at now how this percentage will evolve around the world in terms of percentage, China today has about 50% and will increase to 75% of the Chinese population will be in urban systems. India will go from about 30% to about 50%. Africa will be following similar trend, and OECD will be about the same level. So most of the megacities of the new megacities of the future will be in non-OECD countries. So if we look at the, in terms of where the energy is being used in the urban systems, we see there the distribution of the energy sources across the urban systems between buildings, the transport, industry, agriculture, and power generation and heat. So these are the distributions, and there are details in the publication. In the CO2 emissions, we see that the CO2 emissions are also distributed among the different sectors. So let's look at now in terms of evolution, of projected evolutions in our post-Paris scenario. We see that most of the energy demand growth in the world, the growth will be coming from urban systems in emerging and developing economies. So this is really a very strong focus if we want to decarbonize with the access to a larger population. That is one of the focus areas. So let's look now at the, in terms of what is the potential in terms of decarbonization of the urban systems. In 2014, this is the distribution of emissions between the urban systems and non-urban systems. In a 4-degree scenario, or the NDC scenario, what we see is we see the growth. We will go from the 35 to the 42 gigatons that we discussed earlier, still with quite a significant amount coming from the urban systems. There is a significant potential for reductions, and these are the areas that will be impacted. Power and heat will be the biggest area of influence, followed by industry, and then transport and buildings. And these will be from the urban systems. Then we have reductions also from the non-urban systems. So if we look at the final 2-degree scenario, what we would see is that in a 2-degree world, in 2050, we will have the 15 gigatons of emissions, which would be split 2/3 in the urban, but then we would have gone to 10 gigatons. And non-urban will be at 5 gigatons. And this would be about the split by that time. Let's look at transportation, which is one of the biggest, and we're certainly very pleased that the Imperial College and Grantham Institute are publishing this paper on air quality. We see the transportation that we analyze in one of the chapters, and around the world, these are the different transportation modes around the world. We look, for instance, in the United States, it's split between the small and medium cars to the large cars, and we have air transportation. If we look at Africa, interestingly, the half of the transportation is through buses, and the second one is minibuses. So every area around the world will have a different distribution of activity measured in passenger kilometer with different modes. China is very diverse. If you look at Europe, it's dominated by small and medium cars. So every country would have a different signature in terms of transportation mode. So that's why you need to analyze every area differently. One thing very important is air quality, as was mentioned by Martin earlier. This is the PM10 in different cities around the world, from 0 to over 200. We see different cities around the world in the different continents. So I'll let you guess what is the level that is recommended by the World Health Organization compared to those different numbers. And it's quite striking that the World Health Organization recommendations are met only by very, very few cities around the world, even including Europe. So we look at I think in Europe, one city is significantly below, which is Copenhagen. In North America, it's Vancouver. And in Australia Pacific, it's Auckland. But not many cities like this. And certainly, if you've been to Copenhagen recently, you'll be impressed by the number of bicycles that you see in that city. So we are far from the recommendations, and we just published at the IEA a special focus on energy and air quality that came out in June this year, and this is available also for free download on our website. But you see cities like Delhi or Karachi, it's absolutely terrible. It's about almost 15 times the recommended level from in terms of PM10. These are some of the, and this is from the publication on air quality. These are air quality. We have estimated that from the energy sector, the number of premature deaths that you have due to the air quality, this is including both the transportation and the in-house use of let's say, traditional energy systems, is about 6 to 7 million people around the world. So these are the death rates for in different regions around the world, and you see around the world that it's not only developing economies, but you have a number of economies in Eastern Europe that are impacted by this high mortality rate. And so this is a little snapshot of what's happening on the air quality. So in terms of energy technologies for transportations, we have looked at a number of technologies. This includes the switching and the use of IT technologies, the Ubers, the shared drives, and so on. So all these have been included in the report. We have also looked at the policies, and the policies are not only national policies, they are also local policies, and they need to be meshed together. If you go to a place like Norway, for instance, it's where you have the highest percentage of electric cars. It's because the national government is providing incentives, but also the cities are providing incentives. So you don't pay the congestion charge in Oslo for electric cars. You don't pay for parking for electric cars. You can use high occupancy lanes for electric cars, even with one passenger. So all these are local policies that mesh with national policies. Different examples of policies that we have analyzed there in terms of pricing, regulatory instruments, and the different modes of transportations. So where do we go with transportation? If we go in a Paris, post-Paris world, in a NDC world, in terms of investment in transportation, what we look at, this is today's picture on the left, which is 2015. There is about $5 trillion going to the transportation system between cars, between the infrastructure, and infrastructure includes parking and road, and also includes the metro and light rail. If we go to a 4 degree, what we see is that the biggest growth area would be from internal combustion engines, followed by the parking and road, and then electric cars will be expanding, and there will be a slight expansion of metro and light rail. In a 2 degree, we may ask, so what would be the investment required in a 2 degree? The very interesting story is that actually a 2 degree for transportation costs less. And why does it cost less? There will be more investment in electric cars, but much less on ICEs. Parking and road, we would need less of those, and we would need more on metro and light rail. As a result, we see the difference in investment of about $500 billion between those two cases. So it doesn't cost more from going into a clean transportation system. What does it mean in terms of electric cars? In a 2 degree world, we go from 1 million cars, electric cars today, to 1 billion cars. So it's 3 orders of magnitude. What does it mean in terms of penetration of electric cars? This means that about 40 to 45% of the cars in 2050 would be electrified by that time, compared to 0.1%. So that is quite a significant growth. So a second factor in the cities is heating and cooling, and this is a distribution today around the world for heating and cooling. Heating corresponding to colder economies, colder countries represent the major part. If we look at the NDC scenario, what we see is the biggest growth actually would be coming from space cooling. And this is due to the fact that more and more electricity is coming to areas that have warmer climates. And this is air conditioning and so on. So what we demonstrate here is that actually with we can reduce significantly on heating and cooling, still maintaining comfort levels, and that would be for both cooling and heating through a number of technologies. Cities also represent a significant source for energy generation, and we look at the potential from rooftop PV, from the municipal solid waste, wastewater, and industrial excess heat. So this is the electricity that could be, the potential that could be generated. That is about, I would say, 30 to 35% of the demand. And then in terms of district heat, the potential could be as high as 40 to 45% from self-generation of cities. Finally, we look at cities, the design of cities to avoid the locking, and what kind of systems should be developed in cities to make sure that we go into this energy 2.0 systems, where we have systems that are connected. We have convergence between electricity systems and IT systems, and this would revolutionize the energy systems in cities. So one thing that is extremely important for cities is that you need to have a very good meshing of national policies versus the local policies, and we go through a number of national policies and local policies. How do they translate into each other? And so this is a snapshot of what goes where from those solutions. So in terms of conclusions, the COP21 and 2015 were extraordinary years in terms of energy developments. The cities are an extremely important piece of the puzzle if we want to decarbonize, and especially in emerging economies. And we need to work all together to go to help those cities that would be the mega cities of the future develop a sustainable system. Transportation is a key part. Efficient heating and cooling are also other components. And finally, the collaboration between the industry, the national, the local governments are essential if we want to have a sustainable energy future. With that, thank you very much and look forward to your questions.
Thank you, Kamel. Now, we do have time for a few questions. What I'm going to do is you're going to ask the questions, of course, but we're not recording the audience, so I'm going to have to repeat the question so we get that down. It's all being recorded, and that's how we're going to proceed. So who's first?
Hi, so really good presentation. My name is Jeff Hardy. I work at the Grantham Institute. I'm interested in the total energy demand difference between the 4-degree scenario and the 2-degree scenario. You stated there was quite a big emphasis on energy efficiency in the wedges between. So I was just wondering how the difference in total energy demand looks from a 4-degree scenario to a 2-degree scenario.
Thank you. Just repeat that. So what is the total energy demand difference between the 4-degree scenario and the 2-degree scenario?
So we can look at it in terms of energy demand. We also looked at it in terms of investment. So from energy demand, actually, we will still see some growth of energy demand, but it will be at a much different intensity, energy intensity, than what we have today. And this will be impacting both developed economies and developing economies. There is significant room for growth in terms of energy efficiency, even in developed economies. We have actually looked at, in relation with the Paris Agreement, what could we do to peak the emissions around the world. And very interestingly, in Europe, the number one measure is energy efficiency. So that is in a nutshell. The other thing that we have looked at is if we look at the overall investment that is required between a 4 and a 2-degree scenario, the difference is not that big. So, and we give some estimate by sector. Of some sectors we will see more investment, and some sectors we will see less investment. But as a global, we see about the same numbers. Now, the things that we haven't looked at so far is what the Paris Agreement says, which is well below 2 degrees with the ambition of going to 1.5 degrees. That is, for many of the scientists, still a little bit terra incognita.
For some of these scenarios, in particular, looking at energy efficiency and distributed energy in urban areas, to what extent are you, do you take a view or do you add to the research changes that are needed in financial services to promote that because there's high transaction costs, customer acquisition costs, and so forth? To the extent that innovations or changes in the financial services sector can support that rollout of more energy efficiency retrofits in local energy supply for local energy generation.
Okay, so the question is, what are the changes in the financial services sector needed to supply the funds for the innovations that are required in these scenarios?
That's a very interesting question. If I look at the financial services, you have areas that in the energy sector that are sexy, and some that are not very sexy. If you look at energy efficiency and you go to your bank to finance energy efficiency, it's not something that is going to excite the financial community. And that's something that we have to change. And we have to look at different business models around the world. The needs for the industry in terms of energy efficiency are very different from the consumer side. If you own a building and you want to go to energy efficiency, you have the issues of not only financing it, but also the fiscal incentives to do it. All these have to be meshed together. So to answer your question, I would say that it's going to be a very wide range of response across all the sectors that we looked at, between the industry, the buildings, the transport, and so on. If I look at transportation alone, it's quite interesting to see how the financial mode is completely switching. We used to have traditional models of financing cars through purchases, to now financing cars through leases and long-term leases, or even pay per kilometer. So all these will be transformed. I don't know if I answered your question. It's a very wide question.
It is.
Yeah.
It's interesting that Charlie Donovan in the Imperial College Business School did a nice briefing paper for the Grantham Institute on the cost of finance in this issue. So it's available on our website. You might want to take a look at that. Yeah. Another question here.
Brahim from Statoil UK. I'm wondering if you have some figures on potential stranded assets, fossil fuel resources under the 2 and 4 scenario.
Okay, so the question is, do you have information on stranded assets in these various scenarios?
So it's another very interesting question. In our modeling, there is very little stranded assets, even in the 2-degree scenario. What is extremely important, and defining what stranded assets are, stranded assets would be assets or investment that would become uneconomical, let's say, due to the changing of policies, and they would have to be retired before their normal economic life when they were initially designed. So I would say that in 2 degrees, we don't see much in terms of stranded assets. What we see is a shift. If I take the oil and gas industry, we have the depletion of the oil and gas fields, which is pretty much at 5% per year. So what would happen is that you have this depletion, you still have ongoing investment, but the rate of investment is not going to be in a 2 degree what it would have been in a 4 DS. So, and that would avoid having the stranding of assets. In terms of power generation, what we would see is that the coal-fired power plants of the older generations, there would be no life extension, and we will all replace them with the more, let's say, modern technologies, with ultra supercritical, with CCS, carbon capture and storage.
The question in the back. Yeah.
Do you foresee or expect the 10 or even the renewable energy becoming cheaper than the fossil energy?
So the question is renewable energy going to become cheaper than fossil fuels? Is that right? Yeah.
So, I mean, renewable energy are competing with some of the fossils, like, for instance, in to displace coal. But so far, they're not really competing with oil.
In the future?
Yeah, in the future. So this would be coming through electric vehicles, and electric vehicles using renewable energy. So what we see is that in terms of electricity prices, the numbers that we have seen which are the $30 to, I would say, $45 per megawatt hour. What has happened that drop? A couple of things. One is obviously technology. The second one is the policies, and there are some incentives that have been given. And then the third one is that in renewable, most of the costs are upfront. So if you have, let's say, a financial cost which is significantly lower because interest rates are at their lowest, this certainly helps in terms of financial feasibility of the project. We used to take 7 or even 10%. Now we take much lower. We take 3% on those projects. And that changes electricity systems, which are pretty much depending on the upfront and with very little operation and maintenance going forward.
I guess that's all upfront cost. Have you managed to cost in how much money, sort of loss on productivity and public health and air quality, have you managed to put a sort of numeric value on that as well? Because presumably that could get added to the cost of fossil fuel, which would make the whole situation a different one.
So in the report that we published in June, which is the World Energy Outlook on Air Quality, so we put some estimates on the number of people that are dying primarily due to that. And we have other organizations like the OECD that has put numbers on the cost to society. The World Health Organization is also doing that. So what we are doing is actually showing what is the economic benefit of having a cleaner air scenarios. So we developed a clean air scenario in this publication, which shows that we could reduce the early mortality rate by a factor of 50% going forward, which is quite significant. And if we could talk about return on investment, it's actually quite staggering that we could have a factor of 1 to 30 in terms of return on investment. That's quite significant.
Thank you.
Thank you. Luke Warren from Carbon Capture and Storage Association. I was very struck by your figure in the 2DS scenario which showed biomass being the largest energy source in 2050. And I'd just be interested in any IEA views on some of the supply challenges of meeting that potential biomass demand in 2050. There's a lot of debate around sustainability, challenges with biomass, potential trade-off in biodiversity, food supply, etc. And I guess related to that, in the IEA models, how reliant are you on combining that biomass with CCS to generate negative emissions to be able to deliver the type of emission reductions foreseen in the Paris Agreement?
So the question is, how can we interrogate the issue on biomass a little bit further with respect to supply chains and things, and what is your view on coupling that with carbon capture and storage going forward? Right.
So I'll take the second question first, which is the biomass coupled with carbon capture and storage. We consider that going forward, if we want to meet the Paris Agreement, the technology is going to be even more required, and in order to decarbonize the system to the well below 2 degrees. And we are currently working on the modeling side with a number of organizations to look at what this technology could bring. But this is actually a technology where the energy sector is looking for solution outside of the energy sector. In all what I have presented here, what we were doing in trying to look internally in terms of solutions. CCS is actually within the energy systems. We take the emissions and we store them underground, but we don't go outside. With the biomass with CCS, we go and interact with the agriculture system or the forest systems, and that is actually pushing us beyond our sphere. So that's why we are working with other stakeholders. Now, in terms of the biomass and the potential for growth of biomass, obviously there are a number of issues in terms of the competition with other applications of the biomass. We saw in the 2007, running up to 2007, 2008, the explosion of some food prices due to the competition with the, and so what we will be publishing in the next 2 months, a roadmap or a how-to guide on implementing technologies for biomass and what kind of mix in terms of policy should be considered.
Okay, so that's coming.
Yeah.
Yes, hi.
Thank you very much for your presentation. My name is Charlotte Wolfby. I'm also from Software. I wanted to inquire about what would expedite this sort of change to the 2-degree future. And you talked about policy and the importance of national policies, supporting local policies, and so on. What's required for a 2-degree scenario, and is there a role for carbon pricing?
So the question is, how are we going to motivate and change ourselves into this necessary 2-degree scenario from where we are at the moment?
So carbon prices will be essential in terms, if we want to achieve that, we need to have the mechanism, and carbon pricing will be the key one going forward in terms of helping to switch from coal to gas, and then also supporting the growth of renewable. So on the modeling assumptions that we take for the 4DS or 2DS, you have there embedded carbon pricing. We certainly very much welcome what's happening in China, where by next year there should be a nationwide emission scheme. But this would need to be generalized. So we need to be at the soon at the $40 or $50 per ton, and we need to go beyond that by 2040. We need to be reaching the $100 per ton. We'll be also publishing a book in November called 20 Years of Carbon Capture and Storage. And this publication is actually why we are doing it this year, is that it was exactly 20 years ago that a visionary company called Statoil started the project of Slackner, and which was really very much forward-thinking. But what we realized that after 20 years, for technology that should have been much wider spread, we are not at the level that we would anticipate. So we are providing recommendations in terms of the way forward.
Thank you. At the back.
Hi, thank you, Richard Folland, Inline Policy. I wonder if you could just say something, elaborate on the central importance of the NDCs to all of this, and in particular, how optimistic are you that the NDC implementation is going to be driven along fast enough to generate the sorts of policy measures that we want to see that in turn are going to bring forward your technology innovations and emissions reductions?
Our question is, we have an NDC-focused way forward. How reliant are we on those NDCs, and how confident are you that those are going to change to the level that's required in the future?
That's a very key question. We have done the analysis last year of where the NDCs, and we shouldn't consider NDCs as being a single step. Countries have come with 2 levels of NDCs, depending on the financing, on the availability of financing. So, but even if we take an average case there, we don't see a peaking of emissions in the next 5 years. And so we need to go beyond that. We have come up with recommendations. This is what we call the bridge scenario, which shows that we can decline the emissions, and by 2030, with the bridge scenario, we decrease the emissions compared to the NDCs by about 5 gigatons. How do we do that? Energy efficiency is one key thing, but we also have other things like the removing the fossil fuel subsidies, removing the methane emissions, and renewables would be some of the wedges going there. But to go back to your question, how sure are we on the NDC? I think that the new approach in the Paris Agreement is that there will be a continuous revision of where we are heading and where we were supposed to go. And that 5-year system is certainly a big progress from where we were before. I think that is the key.
Thank you. Okay, we're nearly at our time. Time for one more question. Good, so I can ask it if there's no one who wants to do it. So, no one's mentioned Hinkley Point, so well done, but I'll do it. Mm-hmm. So we've learned a lot this morning on the radio and other outlets that decisions going to be made on Hinkley Point, and I've commentary that I've heard this morning, there is debate as to whether there will be a final announcement or not. But it's been a long saga, as you know. And I've noticed in your scenarios that there is a need for scaling up of the level of nuclear power. I mean, not as substantial as in some other industries, but nonetheless it's still there. How can that scaling up be achieved given the difficulties that we in this country at least have seen with the development of nuclear power?
I think it's a little bit a catch-22 situation where what we have seen recently is the explosion of cost in the nuclear sector. I mean, you look at some of the projects like the one in Finland, the one in France, the costs are way, way higher than what on the EPRs. I think that one of the issue is the technology maturity. I think this could be overcome. Another one is the availability of skills in the nuclear industry. If we go back in history, the big boom of the nuclear sector was in the 70s and 80s. This is where we had a lot of specialists that were being trained. After that, and after a number of events that happened in the 80s and 90s, there was a significant decline. And a lot of that expertise has pretty much retired. I think that we need to replenish this expertise. What we are seeing today, and just to give a number for 2015, there were 10 nuclear power plants around the world that were commissioned. 8 were in China, 1 was in South Korea, and 1 was in Russia. On this side of the Atlantic, nothing. So I think that we need absolutely to increase the visibility of the nuclear sciences with our graduates and make sure that all those creative minds can help in terms of providing safe nuclear solutions at an acceptable price.
Thank you. Thank you. Well, okay, everybody, thanks for your questions, and please stay around for a little bit afterwards to chat to each other, but also to pick up some of the literature that you've heard about. Hopefully that'll be outside. But before we leave, please join me in thanking Kamel Ben Naceur for a wonderful talk. Thank you very much.